So, today's lecture we are basically going to focus on query execution and optimization. So, we will discuss few discuss issues and then few fundamental ideas in this field. This is a vast field and requires a lot of study. So, in this lecture I will basically give you an exposure to the basic issues that are involved in this query execution. So, we know that an SQL query when it is specified, it needs to be converted into a relational algebraic expression tree, and then we have been discussing various algorithms for executing these relational algebra operators. So, we need to choose those operators and then execute the query actually. So, but before we actually go ahead with the actual execution, what is normally done is to take this initial relational algebra expression and then rewrite it in a manner that it is meaning preserving, rewrite it and that rewriting basically takes place using certain heuristics and as well as algebraic transformation rules. So, so I will not go deep into this algebraic transformation rules, but you can imagine we will mention some of them. And in addition to the algebraic transformation rules, we also use certain heuristics and then rewrite this relational algebra expression into an expression which is amenable for execution. So, this can be called as heuristic or algebraic optimization. Now, once we generate that tree, the final relational algebra expression tree, we will also do one more step, which is called the cost based query optimization. Now, for various operators that are there in the relational algebra tree, we have choices of algorithms, choices of what algorithm to use. If there is a join, what is the appropriate algorithm to use in that particular relational algebra expression. So, and if there are multiple algorithms that are applicable for that particular operator, then what is the estimates of the costs of those methods. Okay. So, taking these estimates of the costs of the relational algebra operations and actually if you do one of these operations in one way, some other operation may have to be done in only in a certain way. Okay, they are interdependent, right? The operators are interdependent in the tree. So, taking all these things into consideration, we have to actually formulate that as a optimization problem and then try and get a minimal solution of choices of these methods for all of those operators in a combined manner. Okay. So, and then you generate what is called an execution plan, where you fix as to what method is being used for what operator, and then go ahead execute the query. Okay. So, I will illustrate this the algebraic optimization with a elaborate example. So, we will see that. So, let us focus a little bit on this heuristic optimization. So, the main heuristic rule that we will use is apply the select and project operations before other operations are being applied. That means, from a relational algebra tree point of view, if you find a select operator, try and push it to the leaves. See, what is a relational algebra operator? A tree. At the base, at the leaf levels, we will have the actual base relations that are available on the relational in the database, right? And then two of those relations will be combined using a join, and then the result will go with a projection to some other operator, and that operator will get another operand from somewhere else, and then then some maybe union is applied and things like that. So it all goes like that, right? So at the leaves you have relations basically. Okay. Now one of the heuristics that we will apply is that push these selections and project operators all the way towards the leaves. So if you do that, then right at the initial stage, because you are executing the expression in a bottom up manner, right? You are executing the relation expression in a bottom up manner. So right at the beginning, you would have reduced the number of tuples that go into these operators, right? So with that idea, so we try and push this select and project operators all the way to the leaves, or in other words you need to apply them before you can apply other operators. So if it is possible to do that, right. So that we will see in through an example. So the effect of this heuristic, applying this heuristic, is basically that we will be able to reduce the sizes of these intermediate results. There are a lot of intermediate results. The internal nodes of the relational algebra tree are essentially intermediate results, right? And because projection also is being pushed as close to the leaves as possible, it also reduces the number of fields that are there in the intermediate results. So this is one of the main heuristic rules that we will apply. And then make use of these relational algebra operators. All of them satisfy certain algebraic rules. Like for example, select, project, join, union, intersect, all of them are commutative operations. You can split them around. Okay, they will give the same result when you so two selects have to be applied, then you can apply them in any order. Right, two projects have to be applied, you can do them in any order. So A join B is same as B join A, right. So all those properties are there. So you make use of them and then adjust these operators such a way, and then union, join, intersect, they are also associative. So A join B join C can be written as A join B and then join C, or A join B join C. You can write it either way. Okay. So make use of these associations. Make use of these algebraic rules and do some rewriting if necessary. So there are many more of these. How do these operators interact with each other? There are a lot more algebraic laws that we can express. I am not going to cover them in the lecture, but please read about them. They are very interesting, so you can make use of them. They are not very difficult to understand also. Okay, so basically we will make use of this relational algebraic laws and the heuristic rules, and then do a rewriting of the expression. So and then the cost based optimization will come into picture. Okay, so the issue here is that the relational algebra operator that is there in the middle of the tree somewhere can be evaluated using many methods. We have discussed several possibilities for doing joins and making use of indexes if they are available, like that. There are so many possibilities there. So for each of these methods, we need to have some kind of an estimation of what is the cost we are going to incur if we use that method. So that is what is the cost function. So for all these methods, you can essentially use those formulas that we were discussing as to how many number of block accesses it will do and things like that, and convert them into some kind of a cost function. Okay. So that cost function will take the various parameters like the sizes of the files and then the availability of the indexes, all these things into consideration. Essentially the sizes of the two operands, and then it will give you an estimated cost. And one important thing that we should note here is that these choices have to be made in some sense simultaneously, right. If you make one choice here, that might affect the choice of another method somewhere else, right. So, there are interdependencies between these methods. So one has to cast this as an optimization problem, and then use some optimizers for doing that. So it's actually an intractable problem. It can be shown that it is an intractable problem. So you basically have to use a lot of heuristics, and then you have these different plans of execution. So evaluate them based on these um, individual cost estimates, and then the overall plan cost can be what is the cost of the whole plan with all these choices made at each of these algebra operators, and then choose the plan with the least estimated cost. That is the cost based optimization. And these optimizers can actually sometimes go horribly wrong also, because you are all basing decisions on estimates. We do not really know how the data. Okay. Now let us take an example and illustrate these essentially the heuristic and algebraic optimization ideas with this example. So read this query. The query asks for names and phone details of professors who taught the course as taken by some student with roll number and in the even semester of some year. So it's a simple query. So here is the SQL query for that. So remember that we have professor details in professor relation, and who is teaching what in teaching relation, and then who is enrolled for what course in enrollment relation, and and so we have various conditions now. So the roll number is given. So E dot roll number is CS 08B027, and the E dot course ID should be the one that is being taught by the professor, T dot course ID, and the semester is even, year is 2010 in both enrollment as well as teaching relation things. And then the person who is teaching is who we are interested in. So we will project employee ID, name, and phone of that particular professor. Okay. So this is how typically the where condition is specified, right? So we do not distinguish between which of these things are joint conditions and things like that, but one can actually figure them out. So the initial relational algebra expression that we will write will be simply like this. You know that this is equivalent to the SQL query. Pi p dot employee ID, p dot name, p dot phone, sigma theta p cross t cross e, right. There are three relations involved in the from class. So p cross t cross e, and do this. What is theta? Theta is this entire stuff that we have seen there. Okay. So I have reproduced this entire where condition here. Okay. So that is how the initial relational algebra expression will look like. Now we start a series of equivalences for this relational algebra expression, where we will show how exactly this entire condition has to be placed appropriately inside, and how we convert these operators, etc. Okay. So let us see how it works. So P dot so this is the projection list, and then sigma theta at p dot p cross t cross e, where theta is this entire. Now what I have done here is that this theta that was there in the previous slide, I have regroup the predicates. Luckily for us, it is all conjunctions. So what I have done is to group together the things that involve enrollment, all the conditions that are on the enrollment here, the conditions on the teaching relation here, t dot e semester equal to E1, t dot e equals to thing, and then the other conditions, the remaining conditions I put at theta 3. So theta 1, theta 2, theta 3, I have broken down the same thing into this one. Now after having done that, we know that it is sigma, sigma. So if this is a conjunction, then I can apply them in any order. So I can now write this as theta 1 and theta 2 and theta 3. Then having realized that this this theta 1 is actually applicable to enrollment, I can now kind of push it all the way towards E, because this is what it is. So this theta 1 is completely working on the E enrollment relation. So I can now, I can take this theta 1 that is part of this theta and then push it all the way here. You agree with that? And so similarly, I can push theta 2 to T, because that is completely applicable to the relation T only. Okay, even if you keep it here, we will actually form the cross product and then again do the selection, right. So instead, I can now do the selection and then do the cross product. The cross product and selection can be used in that way. So this is what we do. So theta 3 of course involves P, T, E and all that. So it involves all the 3. So I cannot do anything about that. I will keep it here for the moment. Now in the next slide, actually I will actually break this into ones that involve PT and the ones that involve ET. So I can then the one that is involving E and T, I can actually push up to this, right. Let me see where. Okay. Okay. Now let us break this in, theta 3 of the previous slide into 2, which is P dot employee ID equals T dot employee ID, and then E dot course ID equals T dot course ID. I have broken down that into further 2 predicates. Okay. So having done that, I now realize that this portion of the expression has E and T, and so any condition that is involving E and T can be pushed all the way up to this sub expression, right. So that is what I will do. Theta 4 is having to do with E and T. So I will take the theta 4 and then push it all the way up to here. So I have a new bracket now, sigma theta 4 here, and then I apply it to this one. So now you can see that where this selection conditions are going, they are going down the tree. Okay. Now this theta 3 which has P and T has to remain here, because this is involving P and then something else. So P and T, and so it has to remain. Okay. So I hope it is clear up to this, right. Now now actually we can use this transformation, that the cross product followed by selection has to be replaced by joins basically, right. So now we will do that. So the cross product of 2 relations followed by a join can be replaced by followed by a selection can be replaced by a join. So we will take this as the join condition. So put the join operator here. So theta 2 sigma theta 2 t, sigma theta 1 e will come as it is. Now we have a, between them we have a the join with this theta 4. Similarly here for the result of this and the p, I now apply the join and then write this as join theta 3. So theta 3 is p dot employee ID equals t dot employee ID, which is applicable here, and then theta 4 is e dot course ID equals t dot course ID. So it's appropriately positioned. Okay, so do you get that? So this transformation is actually simple, algebraic, right? So the cross product followed by selection can be replaced by join. Basically, that's what we have done. Okay, so now that we have it, we will now focus on the projections. We will focus on the projections. The projections, uh, in fact, what is it that is required of enrollment? In theta 4, what are the conditions that are there? Course ID and course ID here also. So you basically need course IDs, and from what is theta 1? Theta 1 has conditions about on enrollment and semester year. Okay. So after you do this condition, after you do apply this selection condition, what should it be? What should we project here? Because the only thing that is being used here is course ID, right? So that's what needs to be projected after doing this selection. So we will work that out. So now you see I have introduced projections basically with the idea saying that don't carry any attribute that is not going to be necessary upward in the tree. The simple principle. If you are at some leaf and it is producing some intermediate results, don't carry any attributes upwards in the tree unless it is going to be useful for the tree in upwards. Okay. So theta 1 is all this. So you applied it to enrollment. So the joint condition here requires course ID. So only project course ID. That's all you need. And here from the teaching, you require not only course ID, which is being used here in theta 4, but you also need employee ID because that's what is being used. T dot employee ID is coming somewhere. Theta 3 is coming as, yeah, okay, employee ID is coming up somewhere. So you project course ID and employee ID from teaching, and then you have that appropriate intermediate result, and then from there actually you, after doing this join, you only need the employee ID because that is what is being used in theta 3. Okay. So and then from for P you can keep all the other things because the employee ID, name, phone, all of them are applicable to professor relation. Keep these here. So this is how we will transform and push the projections also down as much as possible into the tree towards the leaves. Okay. So of course I am illustrating the algorithm through an example only, but I just want to get the spirit behind the process. So basically we will avoid carrying unnecessary attributes upwards in the tree, and then use projections to reduce the sizes, the widths of the tuples that we are going to carry. Okay. So this is how this is now you can't do anything more on this particular algebraic expression. So this is the final expression that we have. Now we have to find out how this join can be evaluated, how this join can be evaluated, and how this join can be evaluated, find out the methods for evaluating these things, and then so what you basically also do is, while you are trying to prepare the input for the join, you will read in this relation, right. So you will have to read this relation in order to prepare. So actually what you do is, you combine all these things into an operation, where as you are reading the records, you will apply the selection function, pick up the attribute, and then prepare the result. So you combine and then pipeline the. So obviously it does not make sense to first apply the selection condition, write it back to the disk, and then and then later on do. So what you do here is, you also make use of pipelining idea. So once you start reading records, you see what are all things that need to be done with the records, and then do them all together, and then prepare the results. So once you are prepared these results, probably as an intermediate relation, then you also do this same thing. Then you have essentially two joins to perform, and then you figure out what are the costs, or what are the applicable methods, and make use of these formulas or any estimates that are available in the catalog, figure out what are the costs for the different kind of plans. So the plan here could be that I will I will apply this join first, and then the other join. Actually in this case I do not think we have much choice, because we have to apply this join and then apply this join. But in general, in a query, you may have options of how to execute joins. Fine. So this is what we will do. Is this whole process kind of clear? So essentially, what we are doing is to initially put this entire where clause as the theta condition here, and then break it down into pieces of conditions that are to be satisfied by appropriate components of the expression, and then push them towards the operators, towards the operands, lower down the tree, and then use algebraic transformation rules to replace them by joins, and then go ahead and then finally also push the projections. So so finally the query plan execution is like this. It also kind of depends on the what kind of query that you are handling. But before that, you have to take a call on how to handle this intermediate tables. So you have to take the intermediate tables will come up, right. So depending on the size of those intermediate tables, if you can handle them in memory, you better handle them in memory. If necessary only, you kind of materialize and then actually push them to the disk. To the extent possible, keep it inside, and then do what is called pipelining. So try and apply multiple operators onto the stream of records that are going to come in a pipeline fashion. Now, so there are actually two kinds of queries, right? The compiled queries and the ad hoc queries. See, the compiled queries are the ones that actually sit inside the transactions. The transactions are pieces of work that you want to do in order to carry out certain logical request against the database, right. So it's a program that involve um, shooting several queries to the relational database, getting results, and then probably shooting one more query and things like that. So, you know the queries that you are going to shoot to the thing ahead of time. Okay. So, since you know them, you can actually afford to take that query and then do a lot of whatever optimization that you can do, and then actually fix a nice query plan and then go ahead use that query plan. But as against this kind of queries, if you get ad hoc queries, that means from the terminal you analyst is sitting there and then he or she types a brand new query which you have never seen before because he has some data analysis need, and then and he is expecting results fast. So, you may not be able to do an elaborate optimization in such context. You will have to do some a little bit quick optimization and figure out how fast you can execute that, because there is some performance penalty that you pay while you are doing optimization of a query also, right. So, you will have to work out run some algorithms and figure out and then choose the query plan and all that. So, it takes time, right. So, you also have to have some lighter versions of this optimization, so that you do not where it matters you may have to apply some lighter versions of optimization. Whereas for compiled queries, since you are doing them kind of offline, the optimization can be done offline. The cost of optimization actually itself may not matter much. So, you will, and since these compiled queries are going to be executed some hundreds of times, so you are better off in spending some time in figuring it out as to how best to evaluate that query. Okay. So, that is how this whole it is indeed a vast subject, and a lot of research is actually has gone on and is continuing to be done by relational you know, databases researchers on how to improve this query optimization, because they are in some sense the heart of the whole system. Okay. So, I think with that we conclude this lecture.